Good morning to all. So today we will be discussing different characterization techniques in nanomaterials, which will be used for different nanomaterials. We already has been discussed with the nanomaterials are the materials under below under nanometer. Okay, so these particles are difficult to observe by your naked eye, so you need to use a even to understand from a microscope it is difficult, right? This dimension is 100 nanometer. It is well below the dimension of a microscope. It can see where you can only see the larger particle of size. Okay, so if you want to see the nanomaterial characterization, there are many methods are there. One method we can say that there is a spectroscopic technique. Okay, so we can use the spectroscopic technique which will be utilized for the characterization of a material. So one among it is that is UV spectroscopy. Another one is DLS spectroscopy. Okay, so we'll talk about this thing later. And also there's a technique where you can understand the size of nanoparticle, and also you can see the arrangement of nanoparticle and the morphology, the shape of the particle, and all you can understand by using the imaging methods, which involves TEM, SEM, AFM. Okay, transmission electron microscopy, scanning electron microscopy. Okay, and we have another technique which is called AFM, atomic force microscopy. So in UV spectroscopy, there you will be actually measuring the absorbance with respect to different wavelength of light that you are incidenting there. So that is the figure you can see here: absorbance versus wavelength. So you will be measuring the absorbance of a light by passing the different wavelength of light. That is, you will be taking from near IR to the UV visible region. We will be just taking the all the wavelength, and which wavelength has been absorbed over there and which wavelength is transmitting, that will be can be observed there. Okay, so here you can see the another image which is saying the different nanoparticles which is actually has been characterized by using SEM, okay, scanning electron microscopy. And you can see that from this figure, so the nanoparticles will be having a spherical in shape. Okay, that you can see from this figure. And also from this figure you can see that in certain region the particle is clustered, so it is we call it as agglomerated. Okay, where the clustering of a particle you can see on some side. Okay, and overall you can see that it is in spherical in shape. And also from this figure you can also see the dimension of that particle, that is the size of this particle, by measuring the diameter of this sphere. Okay, from that you can see that the particle size can be also see from the imaging methods like scanning electron microscopy. Now we'll see in detail how do we identifying different techniques. Here you can see that when we talked about different dimension of particles, we have talked especially on a quantum dot. Hope you remember that. Okay, in a quantum dot case we say that the particle size is a well below 2 nanometer, or rather 5 nanometer. Okay, so it is a zero dimensional nanoparticles. So if the size is reducing well below the exciton wavelength, it can consider as a quantum dot. And this quantum dot at different shape. Okay, for a different shape it possesses different color, different size also possess different colors. The color of a nanoparticle solution is basically depend on the nanoparticle size. As I said, the size, if you started reducing from 10 nanometer to close to 1 nanometer or 0.1 nanometer, the particle color, the wavelength of light that is absorbed by that particle size will be different. Here you can see that these all are nanoparticles but different sizes. At different size the light absorbed is different. You can see from the color that is over there. Okay, now we'll see this is a one kind of identification that you can utilize to identify the nanoparticle size, and the same way you can also say that the particle nature. So from by utilizing UV vis absorption, normally UV vis NIR also will be there near IR. infrared. Okay, so it will be also there. So we'll be just talking about that UV vis NIR. We know that the wavelength range of visible light is from 770 to 440 to 400 nanometer, we say. That's the wavelength of visible region. And for UV, it is well below 200, right? To 200 nanometer ultraviolet region and the region I consider. Okay, so it's close to 200 to that region. Okay, so here you can see in this particular figure there are two solutions. One is A, one is marked as B. Okay, in these two solutions, the optical density with respect to wavelength, if I measure, you can see that there is a sharp edge you can see on A, and you can see that B is around 700 nanometer. Okay, so what it means is that for the solution A will be reflecting the light of blue. That's why we able to see the blue in color, the solution, right? Our eyes able to see the color in blue. Okay, and the light that will be absorbed by this A is actually what the light is absorbed by this light is basically or the transmitted light is the blue end. Okay, blue end of the spectrum is absorbed here. Okay, and here you can see in B, you can see this light is reflected by blue light is reflected, and we have transmitted the light that is transmitting to our eyes is the blue one for the case of B. Okay, so this is a representation. You can see that from a UV we will be getting the quantitative measure of a color. So what is the wavelength of the light that is absorbed, and what is the wavelength of light that is transmitted also we will be getting. And this is the experimental setup one will be seeing in a UV spectrometer setup. So this is a schematic setup of that one. Here you can see that we will be having a source light. Okay, so it will be either you can take as a bright light. Okay, and which will be entering through a slit, and it will be passing through a prism. So this prism will allow this light to get dispersed due to the variation of the velocity, and with different frequency of light will be observed here, and this again passing through a slit. Okay, and when it passes through the sample will be absorbing any one of the light. Okay, so which will be getting, since it's close to this slit is placed over here, so we can say that the light will be a monochromatic light will be passing over here. So this is one of the setup where you can keep the detector like this, in this manner. Okay, either in this manner you can see the detection. Okay, in another way what we do here is that we'll be having a source. Okay, so after the source we'll be keeping the sample means we will be having a solution. That solution you can keep on this cuvette. This we call it as cuvette. So we'll be placing the solution, we can drop into this cuvette, and it will be passing the sample, and we have an entrance rate, and we have a dispersion curve. And while you seeing the dispersion curve, if you are keeping on a array, okay, diode array, where you can actually see the different colors over there, and these colors, there will be certain band will be missing, or the band will be darkened in that area, and we can say that if there are some darkened area is there, and that part of the side the light is get absorbed, the light is absorbed in that area, so that we cannot see any corresponding light, so the light will be absorbed there. Okay, so the two setup will be there, and this can be if you have a transparent glass plate, and if you coat some thin films on that, and also you can actually see the absorbance versus wavelength by using UV visible spectroscopy. It is not only the only liquid sample can do this one. No, not like it. We can measure liquid sample, we can do the powder sample, we can do a thin sample also. How do we do powder sample? We can just scrub it, paste it on a slate, a glass slide, then you can take the measurement, or rather you can also make a dispersive solution by using this, and you can do the method also. Okay, so in either way you will be getting the absorbance versus wavelength in a solution, or a powder or a thin film can be measured by UV visible spectrometer. From that one can say that the characteristic absorption peak for a definite case. So that's the one tool. Here you can see that the characterization observe peak for different sample. Okay, and now the another technique which we call it as dynamic light scattering, which is called DLS. So DLS basically what it do is that it is utilized to find the particle size. Okay, which we will be utilizing to find the particle size, as you are doing the technique in a case of lycopodium experiment, where you are actually measuring the particle size using a laser setup, right? On a similar setup, we are doing the same situation. We have a measuring the Brownian motion of the nanoparticles, and we correlating the particle size corresponding to that. So here you can see if there is a particle in a solution have a distribution like this, and we will be putting a laser over here. The corresponding laser will be detected by using a photo detector, and we will be getting the intensity versus the time of motion, and from that we will be getting the nanoparticle size. And here you can see that if the particle size is comparatively lesser, if there are number of particles will be huge, and you can see that intensity versus time profile is it will be entirely different from the earlier one. So for a larger particle, for a smaller particle solution, the intensity profile is giving a different idea. From that, we can actually find the number of so the particle size in that case. Here you can see number of fraction of gold nanoparticles versus particle size is measured by the DLS. Okay, and here you can see if we are exposed for 1 minute and for 3 minutes and for 7 minutes, the number fraction will be different. From that number fraction, we'll be getting the diameter of the in nanometer. You can see that it is 1/200 nanometer, and you can see that the particle will be having the if you see the width of this one and take the median of that, we will be getting that it will be close to 5 nanometer and all it will be coming. Okay, so that's how the dynamic instrument setup will be. So here is a instrument, it is made by Malvern, you can see over here. So it's a company. Okay, so that's a two kind of approach to identify nanoparticle characterization, where you can actually measuring the nanoparticle size and the nanoparticle characterization by means of the wavelength. Okay, so here normally what we do here is that we will need to identify the absorbing wavelength over here first of all. Okay, by using UV visible NIR spectroscopy, we will be finding the absorbance wavelength of that particular sample, and by using that particular sample wavelength, we will be directing that particular wavelength of light towards this one to get the Brownian motion and by correlating the particle size. Okay, so here in imaging methods, so imaging method has either you can do in a normal light to optical microscopic method, where the limit is that you cannot probe only microscopically, you cannot probe where is the size of the particle, and the resolution that you can maximum obtain will be in terms of 1 micrometer or 0.1 micrometer. Okay, but when it comes to electron microscopy, where we already are discussing that when electron is interacting with the matter, so it will be we can actually get the different kind of probable matter interaction will be there. There will be secondary electrons, auxiliary electron, backcharged electrons. When electron is interacting with any matter, so that is we already are discussing in our radiation physics side. Okay, in that discussion we'll be taking two methods here. One is tunneling electron microscopy. The electrons that is tunneled through the material can be obtained by utilizing that technique. We will be having tunneling electron microscopy, where in scanning electron microscopy we will be collecting the secondary electrons that is emitting from the surface of the material, that can be obtained as a further converting as an imaging technique. So that's what we in second scanning electron microscopy SEM. So there's another technique which is called scanning probe microscopy. In a scanning microscopy, we have scanning tunneling microscopy and atomic force microscopy AFM, and we have a profilometry to understand the thickness of the material. Okay, so we have STM. STM is normally used to identify the in-depth imaging, and AFM normally is to find the roughness and the morphology of the surface as well. Okay, so these are the major techniques that is utilized for imaging method. There are subsidiary technique associated with this one also, so we are not focusing on that right now. So you can see TEM, SEM, STM, AFM and profilometer. So here you can see the resolution limit for the light microscope. The maximum magnification one can go is 500x to 1500 x magnification can be go for it for the zooming purpose. And for resolution, the maximum size, the minimal size you can observe by using the light microscope is 0.2 micrometer per size, and the limit is reached by 1930s. Okay, and the nowadays we have a light microscope, even you can probe one much more less than also, and also you can attach my photography also there. You don't want to see the object by your eyes, and you can keep the memory in that. We can take a picture by using a attached photographic setup also, camera also there in a light microscope in nowadays. Okay, so we have a resolution which is depends on mainly the wavelength of the illumination light. Okay, and the numerical aperture of the lens you are using. Okay, so here you can see the D is equal to 0.612 lambda by Na, where Na is the numerical aperture and D is the distance, and lambda is the wavelength of light that you are using. And from the D, you can see the diameter, the size of the particle that is we are dealing with is highly depend on the lambda and numerical aperture. So the another technique, that is electron microscope. The electron microscope, the wavelength of electron, we know that wavelength of the any particle that is using should be comparable to the size of the particle that you are experimenting or observing, right? So that's very important key in that one. So the wavelength of the electron that is using in electron microscope is mainly depend on the mass of electron, mass of charge, and the electron charge, and the potential difference that is need to accelerate the electron from the electron beam to the surface of the atom, the material you need to investigate. So we have lambda is equal to h by root 2 mqv, where q is the charge and v is the voltage are you applying, and m is the mass and h is the Planck's constant. So this is how the lambda depends on the different quantity. From the equation itself, you can understand that the mass has a dependency, the charge has a dependency, and the voltage has a dependency on lambda of a wavelength that you are using. So this is the first setup based on electron microscopy, that is we call as transmission electron microscopy. So here what we are having is that we have an electron gun which is made up of a tungsten or any other that. The purpose of it is that it is to send the electrons. The electron beams need to send by this one. Okay. So in order to generate the electrons, we will be applying high voltage, and we have a condenser lens to focus the electron. So this is made up of magnetic condenser lenses, and which the purpose is to focus the electrons in the proper path and to direct towards the sample that is placed on the bottom side. Okay, so here we will be having a fluorescent screen and beam, and we have an electron beam. Okay, we have an objective lens and the specimen holder and analog and condenser approach, and second condenser lens and condenser approach, and first condenser lens. So the electrons will be getting will be there, and will be focusing on the camera over here. Okay, so what happens is that when an electron beam strikes on the sample, which will be transmitted through the sample as well, and the scattering will be occurring in that situation, and the unscattered electrons, of course, the unscattered electrons will be only transmitting through the sample, and that will be detected using the fluorescent screen on the camera that is placed well below the sample. Okay, so the sample will be somewhere here. Okay. So this is a picture of a transmission electron microscopic setup. This is a schematic setup where we have marked all the different elements that is using in the setup. Okay. And here this is the experimental setup or the characterization setup for the transmission electron microscopy that you can see in a different lab. And normally we will be using the copper grid sample holder. So in this grid we will be keeping our powder samples. Okay, so the importance of term, the difficult part of term is that the sample preparation for term characterization. So there is a special kind of preparations are there involved to the characterization of term. Okay, so that's a one thing. And here you can see the term images, different term images that is obtained for organic and inorganic material. And you can see that for inorganic material, the well-ordered structure can be actually obtained by using the transmission electron microscopy. So it has a very high resolution compared to the scanning electron microscopy. It has a very high resolution image can be probed. So this is a kind of atomic arrangement one can easily probe through this setup. So there is a very advantage of transmission electron microscopy. And now it comes to scanning electron microscopy. So here also we have an electron emitter gun will be there. Okay, and we have a condenser lens to focus the electrons towards the sample, and we have a diffraction coils and final lens, and the sample will be the specimen will be placed here, and the electrons will be interacting to the sample, and there will be electrons will be scattering with the sample surface, and the scattered electrons will secondary electrons will be collected by using a electron detector, and this electron detector will be connected to an amplifier to amplify the signal from the electron detector, and further which will be attached to the screen, and here the image buildup will be doing that. Okay, so this is the same layout and its function is properly mentioned here. Again, the electron beam strike the sample and the electron penetrate to the surface. The interaction occurs between the electron and sample, and the electrons and photons will be emitted from the sample, because we know that when an electron entering to that, there will be an ionization can happen, and this further ionization can tune photons to electrons can move from one shell to another shell, and there will be probably photons like X-ray photons will be emitted also there. Okay, so we will be collecting either the emitted electron or photons can be collected in order to identify the imaging purpose. So either you can collect the electron on the detector or photons to be characterized in this way. And in this one, you can see that a particular setup of scanning electron microscopy you can see here, and the figure of a conidia of Aspergillus. You can see that over here there's some image of that particular sample, where you can see that different morphology like a flower like morphology you can see when you deeply see the scanning electron microscopic image of that particular sample. Okay, so this is the sample, and you can see that on the sample image you can see the bottom scale 20 micrometer, and this 20 micrometer says that this first scale, the smallest scale is 20 micrometer here. So if you want to see the size of the particle, you need to take the each one and take it to the multiply of this 20 micrometer, then you want to get the size of one of the particle. Okay, and this is a different spheres, silica oxide spheres, silicate spheres, that is we have already have seen in the first slide regarding the imaging method when we saw. Okay, and this is a circular plant in the SCM image ആണ് ഇവിടെ നമുക്ക് കാണാൻ സാധിക്കുന്നത്. അപ്പോൾ മൈക്രോമീറ്റർ സൈസിലുള്ള പാർട്ടിക്കിൾസിനെ നമുക്ക് ഐഡന്റിഫൈ ചെയ്യാൻ പറ്റും. Here you can see a 500 micrometer. This 500 micrometer saying is that this up to this length, okay, this length, the scale value is 50 micrometer. That's the region. Okay, so the scanning electron microscopy of a hair split end. Okay, and a bug eye microscopy, you can see that kind of bug means like the mosquito or any some bug, right? So bug in the eye. Okay, bug in the eye and the scanning electron microscope, you can see like this. Okay, so basically the scanning electron microscopy which feedback from automatically different tip, many type of feedbacks are there. Okay, and there's another technique we call AFM. AFM, so we'll be having the forces between the sample and tip. Okay, we will be measuring, and in STM we will be measuring the tunneling current between the sample and the cantilever tip will be measuring here. And here you can see in scanning tunneling microscopy, the tip scan just above the surface edge. Okay, so electrons have a small probability of escaping a material to the tip. Okay, then it will be creating a tunneling current, and this tunneling current is depends upon the distance between the tip and the sample. So you can see this red one, say the tip edge. Okay, and it will be having a relation Hooke's law. Force is physical minus kx എന്ന് പറയുന്ന law പ്രകാരമാണ് ഇത് വർക്ക് ചെയ്യുന്നത്. സോ ഈ ഒരു ടിപ്പ് ഈ ഒരു സാമ്പിളുമായിട്ട് എൻഗേജ് ചെയ്യുമ്പോൾ അതിനെ നമുക്ക് മൂവ് ചെയ്യാൻ വേണ്ടി പറ്റും. അതിനാണ് നമുക്ക് പീസോ ഇലക്ട്രിക് ട്യൂബ് നമ്മൾ ഉപയോഗിക്കുന്നത്. ആൻഡ് കൺട്രോൾ വോൾട്ടേജ് നമ്മൾ കൺട്രോൾ ചെയ്യും. സോ ഇവിടുന്ന് വരുന്ന സിഗ്നൽ ടണലിംഗ് കറണ്ട് നമ്മൾ എന്ത് ചെയ്യും, ഒരു ടണലിംഗ് കറണ്ട് ആംപ്ലിഫയർ കടത്തിവിട്ട് വിൽ ബി ദ ഡിസ്റ്റൻസ് കൺട്രോൾ ആൻഡ് സ്കാനിങ്. ഇപ്പോൾ ഡിസ്റ്റൻസ് നമ്മൾ എന്ത് ചെയ്യും, ഒരു സർട്ടൺ എഡ്ജിൽ നമുക്ക് മെയിൻറ്റെയിൻ ചെയ്ത് പോയിട്ടില്ലെങ്കിൽ എന്ത് ടിപ്പ് പൊട്ടിപ്പോകും. അതുകൊണ്ട് തന്നെ നമുക്ക് സർട്ടൺ സൈസിൽ മെയിൻറ്റെയിൻ ചെയ്തിട്ട് അതിൻ്റെ കറണ്ട് മെഷർ ചെയ്തിട്ട് വേണം മുന്നോട്ട് പോകാൻ. അതാണ് നമുക്ക് ടണലിംഗ് കറണ്ട്. അതിൻ്റെ ഡാറ്റ പ്രോസസ് ചെയ്തിട്ട് നമുക്ക് വിൽ ബി ഗെറ്റിംഗ് ഇമേജ് നമുക്ക് കാണാൻ പറ്റും. STM ഇമേജ്. STM ഇമേജിന്റെ പ്രത്യേകത ശ്രദ്ധിച്ചാൽ അറിയാം. ഇവിടെ നമുക്ക് ഒരു ആറ്റോമിക് റേഞ്ച്, ഓക്കെ, ആറ്റംസിന്റെ പ്രോപ്പർ ആയിട്ടുള്ള അറേഞ്ച്മെന്റ്സ് നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും. ഓൺ അലോയ് സർഫസിലുള്ള പ്ലാറ്റിനം നിക്കൽ ആറ്റംസിന്റെ അറേഞ്ച്മെന്റ് നമുക്ക് കൃത്യമായിട്ട് മനസ്സിലാക്കാൻ എന്ത് ചെയ്യും, ഇൻഡിവിജ്വൽ ആറ്റംസിനെ ഐഡന്റിഫൈ ചെയ്യാൻ നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും, STM യൂസ് ചെയ്യാൻ പറ്റും. STM ചെയ്യണമെങ്കിൽ നമുക്ക് ഹൈ വാക്യൂം വേണം, ലോ ടെമ്പറേച്ചറിൽ നമുക്ക് വേണം ചെയ്യാൻ. എന്തുകൊണ്ടാണ് അങ്ങനെ? അതിന്റെ കാര്യത്തിലുള്ളൂ, ലോ ടെമ്പറേച്ചറിലാകുമ്പോൾ ആറ്റംസിന്റെ മൂവ്മെന്റ് തെർമൽ മോഷൻസിന് കാരണം ഉണ്ടാകുന്ന മൂവ്മെന്റ് വളരെ വളരെ കുറവായിരിക്കും. സോ ആറ്റംസ് വിൽ ബി മോസ്റ്റ്ലി സ്റ്റേബിൾ ആയിരിക്കും. എന്ത് ചെയ്യാം, മോസ്റ്റ്ലി സ്റ്റേബിൾ ആയിരിക്കും. സോ ഇറ്റ് ഈസ് ഈസി ടു ഐഡന്റിഫൈ ദ അറേഞ്ച്മെന്റ് ഓഫ് ആറ്റം വിത്തിൻ എ സെൽ. And also we need a high vacuum to avoid the maximum dust particle to perform this experiment. Okay, so scanning tunnel microscopy in ഒരു സെറ്റപ്പ് ആണ് ഇവിടെ കാണുന്നത്. ഇറ്റ്സ് one of the finest setup to understand the atomic level imaging of a sample. And now we'll talk about atomic force microscopy. So here the tip will be scanning through the surface and the laser will be reflective of the cantilever movement. This is a cantilever with tip. So the movement of the cantilever movement will be sending a laser light, and which will be reflecting to the photodiode placed here. And here you'll be having an XYZ scanner so that this tip can move in either direction. Okay, and we will be having a feedback loop to change the tip to sample distance. അപ്പോൾ ഡിഫറെൻറ്റ് ഹൈറ്റിൽ വരുമ്പം അതിൻ്റെ സാമ്പിളിൻ്റെ ഡിസ്റ്റൻസ് അത് ഓട്ടോമാറ്റിക്കലി അഡ്ജസ്റ്റ് ചെയ്യാൻ വി ഹാവ് ഫീഡ്ബാക്ക് കൺട്രോൾ. കാരണം നമുക്ക് ഓരോ ഹൈറ്റിനും കറസ്പോണ്ടിങ് ആയിട്ടുള്ള വോൾട്ടേജ് ഉണ്ടാകും. ആ വോൾട്ടേജ് ഫീഡ്ബാക്ക് എടുത്തിട്ട് നമുക്ക് എന്ത് ചെയ്യാം, അതിൻ്റെ ഹൈറ്റ് ഓരോ സ്റ്റേജിൽ വെക്കും. ഓരോ ഹൈറ്റിലോട്ട് പോകുമ്പോൾ അത് ഡിഫറെൻ്റ് ഹൈറ്റ് ഐഡൻറ്റിഫൈ ചെയ്യാം. സോ ഹൈറ്റ് ചേഞ്ചസ് നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും, റെക്കോർഡ് ചെയ്യാൻ പറ്റും. അത് വെച്ചിട്ട് നമുക്ക് എന്ത് ചെയ്യാം, റഫ്നെസ് ഓഫ് എ ഫിലിം കാൽക്കുലേറ്റ് ചെയ്യാൻ പറ്റും. ഓക്കെ, സോ ദാറ്റ്സ് എ വെരി ഇമ്പോർട്ടൻറ്റ്. റഫ്നെസ് ഓഫ് എ ഫിലിം എന്ന് പറയുന്നത് വളരെ വളരെ കുറവായിരിക്കണം ഒരു ഡിവൈസ് ലെവൽ ഫാബ്രിക്കേഷൻ്റെ കേസിലോട്ട് പോകുമ്പോൾ. ഓക്കെ, അപ്പോൾ ആ റഫ്നെസ് ക്യാരക്ടറൈസ് ചെയ്യുക എന്ന് പറയുന്നത് ഒരു ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള ടൂളാണ് തിൻ ഫിലിമിനെ ഡിവൈസ് ഫാബ്രിക്കേഷനിലോട്ട് ഇൻകോർപ്പറേറ്റ് ചെയ്യുമ്പോൾ. ഓക്കെ, അതിൽ ബേസിക് ആയിട്ടുള്ള സ്റ്റഡീസിൽ വരുന്നതാണ് അറ്റോമിക് ഫോഴ്സ് മൈക്രോസ്കോപ്പി എന്ന് പറയുന്നത്. സോ യു ക്യാൻ സീ ദ അറ്റോമിക് ഫോഴ്സ് മൈക്രോസ്കോപ്പി ഓഫ് AFM cantilevers and force tip. Okay, and this is the atomic force microscopy. So the nanosurf EC scans are there, and the butterfly wing can. So ഇവിടെ നമുക്ക് ഈ രണ്ട് ഫിഗർ വെച്ചാൽ അറിയാം, നമുക്ക് ഒരു സാമ്പിളിലൂടെ കടന്നു പോകുമ്പോൾ അവിടെ എവിടെയാണ് ഹൈറ്റ് ഉള്ളത്, എവിടെയാണ് ഡൗൺ ഉള്ളത്, എന്നുള്ളത് കൃത്യമായിട്ട് നമുക്ക് മനസ്സിലാക്കാൻ പറ്റും. ഇത് വെച്ച് നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും, ആ പാർട്ടിക്കിളിന്റെ റഫ്നെസ് നമുക്ക് കാൽക്കുലേറ്റ് ചെയ്യാൻ വേണ്ടി പറ്റും. സോ ആ റഫ്നെസ് കാൽക്കുലേറ്റ് ചെയ്തിട്ട് we can see the imaging of that. And here you can see ഈ ഒരു AFM ഉപയോഗിച്ചിട്ട് വേണമെങ്കിൽ നിങ്ങൾക്ക് തിക്നെസ് കാണാൻ പറ്റും. നമ്മൾ സ്ക്രാച്ച് ഇട്ടിട്ട് അതിലൂടെ നമ്മൾ ആ സർഫസിലൂടെ നമ്മൾ ടിപ്പ് കൊണ്ടുപോയി കഴിഞ്ഞാൽ ആ ഹൈറ്റ് ഡിഫറൻസ് ഉണ്ടല്ലോ, ഇവിടെ നിങ്ങൾ കാണുന്ന രണ്ട്, ഇത് നമ്മുടെ ഹൈറ്റ് ഡിഫറൻസ് നോക്കിയിട്ട് നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും, we can say the thickness of the sample that is you are coated on a thin films. ഇപ്പോൾ ഈ AFM നമുക്ക് നോർമലി തിൻ ഫിലിംസിന്റെ കേസിലാണ് ചെയ്യാൻ പറ്റുക. നമുക്ക് ഏത് കൈൻഡ് ഓഫ് മെറ്റീരിയൽസും മെറ്റൽസോ അതല്ലെങ്കിൽ സോ പോളിമേഴ്സോ ഏത് നമുക്ക് എന്ത് ചെയ്യാം, വി ക്യാൻ യൂസ് ബൈ യൂസിങ് അറ്റോമിക് ഫോഴ്സ് മൈക്രോസ്കോപ്പി. വേറെ സെമ്മിന്റെ കേസിൽ നമുക്ക് ചെറിയൊരു ലിമിറ്റേഷൻ ഉണ്ട്. സെമ്മിൽ നമുക്ക് കണ്ടക്റ്റീവ് സാമ്പിൾസ് ആണ് ഏറ്റവും വയബിൾ. നമുക്ക് ഓക്സൈഡ് സാമ്പിൾസും ചെയ്യാം, പക്ഷെ അത് നമുക്ക് എന്ത് ചെയ്യണം, പിന്നീട് കോട്ട് വിത്ത് ഗോൾഡ് കോട്ടിങ് ചെയ്തിട്ടാണ് ഇത്തരം സാമ്പിൾ നമ്മൾ ചെയ്യാനുള്ളത്. ഓക്കെ, സോ പ്രൊഫൈലോമീറ്ററിന്റെ പേർപ്പസ് എന്ന് പറയുന്നത് ടു ഫൈൻഡ് ദ thickness. So it is a 0.5 nanometer resolution in Z direction. So which we allows to find the profile and structure of a material. And this is a 3D profilometer where you can simply see the thickness, the difference between two layers. Identify ചെയ്യാൻ വേണ്ടിയിട്ട് പറ്റും. Okay, so these are the different characterization techniques we need to talk about. We mainly talked about transmission electron microscopy, scanning electron microscopy, and we also discussed regarding the profilometer, atomic force microscopy, and scanning tunneling microscopy. Okay, with that, the characterization session, that is a part of the discussion for the 5th module of your material science, also we discussed. For any detailed discussion demanded on any particular session, we will be doing that later on. Okay, thank you.